You're so good, James.
Hey guys, thank you, Burke. My name is James Albano, and today I want to go over the ranking cycle, and specifically for Group 1, which is the experiment we're going to do next week. So what's the objective of the day? So first I want us to understand the ranking cycle. So to quote the manual, it's a theoretical process that is still used today for the production of most of the world's electrical power. So you guys can see how important and how useful it is, something to understand. Another objective of the day is to understand the technical components of the cycle. So not only what's happening to the fluid, but also what's making that happen. And we want to be able to calculate the efficiency of the cycle. So without further ado, let's get right into it. So first I want to talk about the steps of the ranking cycle. So step 1 is water being pumped into the boiler. So you can see that here, through this pump. We'll talk about this in a second, but it's crucial at this point that it's liquid water. In the second step is water being changed into high pressure steam. So it goes through a steam generator, and it needs to turn into the steam so it can run the turbine. So second step. So 1 is the pump, 2 through the generator, steam generator, heat exchanger here. 3, then steam shoots up the nozzle and turns the turbine, which produces electricity. So you guys can see this depiction here. It's pretty simple, but basically the important thing to note is that at this point it needs to be gas, or it needs to be steam. Otherwise it could hurt the turbine. So, and that's how those work. And then lastly, after it loses the pressure, through this turbine, it needs to be turned back into water through a condenser. At this point, the cycle starts over again in this closed cycle. It can be pumped. Again through the steam generator. So the technical components. So like I said, I want to explain the technical components. The first is the pump. The pump is isentropic, and this is the formula for the work here. You have the turbine, which is also, so these are the 2 isentropic, and these are the 2 isothermal. So the turbine and the pump, which is going to be the components that have to do with the work of the system, are isentropic, and then the heat, the components that have to do the heat of the system itself, the steam generator, and the condenser. So you guys can see here, the first step. So let's look at this graph first. First step starts isentropic as it raises in temperature, and then it's isothermal. It goes down through the turbine, through to step 4, and then condensed back. Like I said, one thing that I just thought was interesting and I want to pay special attention to is the fact that it needs to be condensed here, both for like the diagram, but also from the practical purpose of you can't have air going through the pump. If you guys remember me talking about the centrifugal pump, I talked about the cavitation and the different problems there in my 6-minute talk. So it's this added kind of importance of making sure that everything is like either at this point condensed, and then before it goes into the turbine, it's raised to steam. So this is ideal cycle, and then this is a picture that I found online of like a real cycle of it. And so basically the main difference that I want to point out to you is that in real life things aren't reversible. So here, whenever the S remains constant, it can go like back and forth. Well, that's not really possible in real life, and that's why you see here, whenever you look at the real cycle, it slightly changes. This should be a mess. It slightly changes here to the right, because it's not completely reversible. And then, like I said, one of the objectives of the lab, so we went through the cycle, what it is, and we went through the technical components. And then lastly, going through finding the thermal efficiency. So the formula is work done in the cycle divided by work added, or work of the cycle divided by, I guess, the Q added, the heat put in, right here, to the steam generator. And so the work of the cycle is going to be the work of the turbine plus the work of the pump. When I was doing this for the first time, I messed it up just because I did work of the turbine minus work of the pump. So just try to be consistent with your signs, because the work of the pump, you're going to be putting work in, and then the work of the turbine, you're going to be having work be put out. So it's going to be consistent as long as you're consistent with it. And this is the formula for it. The work of the turbine, and then plus the work of the pump here. And the Q added is just has to do with the steam generator. And so basically the sample calculation from this lab that we're going to perform, or I guess if it was running, what we would perform, is you get information that you can get from the steam tables. I'm sorry, you get information, and then using the steam tables, you can find the H values for the different pump, variables. And so these are, just looking through my thermo book, found some experimental H values. And then putting it through the formula, we can get 37%. These are just arbitrary values that I found, but it made it kind of realistic. So as far as like, when it would raise or lower. So I don't remember what you guys got. My guess is that it's probably not this high, but that would be, it'd be nice if it was. But that's like an experimental value. And then finally, talk about ways we could increase the efficiency. And one is reheating it and being able to get more work done. And then another thing that I didn't put here is changing the efficiency of the turbine so you can get more work done by the turbine itself, which would raise the efficiency. Any questions? Okay, thanks guys.